Okay, so we're going to continue our discussion of integration. We did an example of a closed surface integral last time, and we said we wanted to now do an example of an open surface integral this time around. So example. So say you want to integrate this field, A equals 5r phi, and this is given in the cylindrical coordinates, in the cylindrical coordinates basis. So if you try to envision this in 3D space, this is the sort of field that is, you can see, is proportional to r, right? Proportional to the distance r from the z-axis, the r coordinate. So the farther we are, the bigger the field, right? And it's always in the phi direction, which is this direction. So the field will look something that's like something that's rotating around the z-axis. Because at any point in space, it has only a component in the phi basis direction, and it doesn't depend on anything else. It only depends on r. So the farther you are away, the bigger the field is going to be, but it's going to be like a swirl around the z-axis. Right. So this is the field, and we want to integrate it along a surface. And what is that surface? That surface is like a slice, like a surface like that. That's essentially from z minus 3 to z equals 3, and then r from 0 to 1 at a certain angle phi. So this kind of surface, slice of surface, this page, imagine it to be a page embedded in 3D space at a certain angle, right? This is at an angle of phi. The idea is that what is the flow of that vector field into this surface. So this is a sort of problem where we can apply integration in this case. So the word we use for this sort of flow is flux. So what is the flux through the surface? The surface is r larger than 0, less than 1, z larger than minus 3, less than 3, and phi is constant. All right. Yeah. So this is a surface integral. We're summing on a surface A dot ds. Now the question is, what is ds? Because we're using cylindrical coordinates, any small surface element here is always also going to be pointing towards phi hat, right? It's always going to be pointing towards phi hat. If we had some other kind of coordinate, it would be more complicated. But any small surface element on the sheet of paper is always going to be pointing towards phi hat. So ds vector is just going to be, and what are the sides of this small element? It's going to be dr dz, right? Phi is not changing. So this is going to be dr dz phi hat. So it's a simple surface element. It doesn't have 3 components, only has 1 component. So we can easily do now the dot product. This is fortuitous because phi hat dot phi hat is 1, right? So phi is just the surface integral, and I'm gonna do it as a double integral now. 5r phi hat dot dr dz phi hat. Phi hat dot v hat is 1, so I end up with 5r dr dz. Assuming I start integration with r. So where is r going from? R is going from 0 to 1, and then that's the idea of double integration from multivariable calculus. You're summing across a surface, but you instead of summing across a surface randomly, first you sum across a line, right? So you sum across r. So you sum across a line where z is constant, and you sum across multiple lines, and then you sum the lines up to get the surface integral. That's why this is called the property of the separation of a double integral or a triple integral or essentially any multivariable function of a multivariable function. You can integrate it in this way. So I can start by going r from 0 to 1, and then z goes from -3 to 3. And this is a simple integral to do. So this is going to be -3 to 3 r squared over 2, evaluated from 0 to 1. So this is going to be 1/2. 1/2, yeah, 1/2. And then what's remaining is 5. Integral of this is dz. What's the integral of dz from -3 to 3? That's just z evaluated at -3, at 3 minus -3, so that's 6. So this is multiplied by 6. So essentially, it's going to be 5 times 3. 5 times 3 is 15. So this would be the flux along this surface. So let's spice up this example. So this is an example of a surface integral over an open surface. Let's do a closed surface example, right? So example. We want to do the same problem, but now we want to integrate along. We want to find the flux going out of an enclosed surface, and that surface is a wedge. So how would the wedge be? The wedge would be something like this, 2 sheets of paper with an angle between them, right? So it would look something like this. So z is still going from -3 to 3, right? And then I have my first sheet of paper, right? And then I have a second sheet of paper towards the back, right? And then I have this kind of circular arc between them. So this is a wedge. Imagine it to be like an orange wedge, only flatter at the top and the bottom, flat at the top and the bottom, right? So this is kind of like a wedge. And then the front piece of paper is at phi equals pi over 4. The back sheet of paper is at phi equals pi over 2. So it's farther in the back. So we want to do the surface, the flux of the field A equals 5r phi hat going out of that wedge. If there is this field which represents a flow field, let's say, of water, how much volume of water would be leaving the surface of this wedge? How many surfaces we have to worry about here? 1, 2, so the front and the back, so there is ds1. And then there is the back, ds2, I'll draw it like this, ds2. And then there is the side, right? So this is the top, bottom, and the side. But do the top, bottom, and the side matter? Bless you. No, the top and the bottom do not matter. And there's a reason they do not matter. Because the field everywhere, at every point in space, its magnitude is a function of r, but its direction is always in the direction of phi hat. Right? So this is A here. This is A here, this is A here. So the field will always be embedded within the top and bottom surface. So what would be the angle between the ds of the top surface? So the ds of the top surface, let's call it this, ds top, t. They will always be at 90 degrees, right? So if you dot any two 90 degrees vectors, they're always going to be 0. Same story with the bottom of the wedge. So the top of the wedge and the bottom of the wedge don't matter. When you integrate over them, you get 0. What about the side of the wedge? It doesn't matter too, even on the side of the wedge, because here let's call this ds side. On the side of the wedge, the ds, the surface element, is always pointing 90 degrees outwards, right? While phi is always embedded within the surface, so it's also 90 degrees. So the sides won't matter. The only two surfaces that matter are the front surface and the back surface. So in this case, we can divide this closed. Notice I'm using sometimes I'll do this, but I prefer to kind of do this. It's understood that this is a surface integral. So I'm subdividing the total closed integral. This circle represents closed as two integrals now. as integral over S1, this is S1 and the back is S2, of 5R phi hat dot, the front ds1 is in the opposite direction of phi hat. Phi hat is in this direction, right? Because that's the direction where phi is increasing. So this is going to be minus dr dz phi hat plus S2 5R phi hat dot, in the back surface, it's just going to be dr dz phi hat. And now this turns into minus surface integral S1 5R dr dz. I think we found that the last time. It turned out to be 15. Plus surface integral S2, also 5R dr dz. So this is going to be minus 15 plus 15, 0. So the flux coming out of this surface is 0. This tells you that if this is an example that represents a flow of water, that tells you there are no sources of water inside this surface, in the volume enclosed by this surface. Everything, because the flux out of the surface is 0, meaning anything coming out of the surface at one point must have come in from somewhere else at some point. If this was something other than 0, that will tell us that there is some source of flow inside the surface, like a pipe or something, I don't know, some source of water. Okay, so that's the surface integral. And again, this is the particular kind of surface integral where we are, it's a flow surface integral. There are other kinds of surface integrals where you have a mass distributed on a sheet of paper, mass density, and then you integrate that. So we encounter those kinds of, that is just a scalar integration, does not involve the dot product. All right, so now we want to move and close the subject of integration by discussing the third kind of integration in 3D space, which is the volume integral. And again, there are multiple kinds. There are multiple types. Right? So typically, we write the volume integral as follows. W does not mean work. I guess I could use a different constant, Q. People think Q means charge. No, I don't know. M. M, some constant. That's it. So it's the integration over a volume of W dV. So this is the volume element, dx, dy, dz for the Cartesian system. Right? And this is some scalar volume density function. For example, the volume element is meter cubed, right? The scalar density function could be kilogram per meter cubed. So you multiply kilogram per meter cubed by meter cubed, you get kilograms. And then you sum up across the whole space and you get some total mass. It could be charge. Like when we study charges, the units for charges are coulombs. So it could be coulomb per meter cubed, something like that. And then there's a second type. There is... we don't have to integrate a scalar. Similar to line integral and volume integral, we examined integration of a vector function. We examined integration of a scalar. We studied mainly the integration of a dot product of a vector with another vector with the line element vector, right? But similarly, here we could just sum vectors and get a result that's a vector. So I could, over a volume, take a vector, sum it up, and then my result is some sort of vector. Let's call it capital P, small p, capital P. Right? So in Cartesian coordinates, capital P would be just, I could decompose this. I could write P as Px, x hat, plus Py, y hat, plus Bz, z hat. I can always take any vector and decompose it into its components, vector components. So doing that, plugging that in, this in, and applying the linearity of integration, I can say essentially that this sort of integral is equivalent to 3 scalar integrals. So it all falls back to the scalar integral, right? So this is equivalent to px dv, x hat, plus py dv, y hat, plus pz dv, z hat. This is only true, by the way, for Cartesian coordinates. Why? Notice I did something tricky here. I did something tricky. I decomposed P into its vector components, and then I applied the integration, volume integral, and then I took the x hat and y hat and z hat outside the integral. I could do that in Cartesian coordinates because, remember, we said the basis, the x hat at this point, is the same as the x hat at this point. Wherever in the volume, in the total volume where you are integrating, wherever you are, x hat is a constant, y hat is a constant, z hat is a constant. So you can take it outside of the integral. If this was some other basis, I couldn't do that. I cannot take the x hat, y hat, the r hat, phi hat, z hat out, because, well, I can only take the z hat out, because z hat is the same everywhere. Because r hat, if this was spherical coordinates, r hat would be at this point this. At this point it could be this. It's a totally different vector. It depends on your point in space. At this point it is this. That's why you cannot take it outside of the integral. I can take it here outside of the integral because it's a special case. It's Cartesian coordinates. Again, I mean, the best way of doing integration at any level, whether it's calculus or multivariable calculus or here, is to practice it. I mean, you can talk about it for a million years, but if you don't practice it, you don't get anywhere. So let's practice a bit of problems. So let's do something to do with the scalar volume integral. Right? So we want to calculate the volume of a section of a sphere. So let me see, this is going to get hairy. Let me see if I can draw this properly. So we want a sphere, of course, in three-dimensional space. A sphere equation is x squared plus y squared plus z squared equals 16. So this is a spherical shell with a radius of 4. Right, so this has a radius of 4. And this is a sphere. Let me draw a sphere as best as I can. Right. So the idea, this is a shell, spherical shell. The idea, what is the volume inside this sphere, but not just inside the sphere. Inside, let's say the sphere is cut by 2 planes. The sphere is cut by a plane y equals 0. So this is y equals 0, meaning x and z can be anything, but y is fixed to 0. And then z equal 2. So there's a top here at z equal 2. So this is intersecting, let's say this is intersecting here at y equals 0. This is intersecting at z equal 2. And then there are 2 last surfaces between x equal -1 and x equals 1. So this is kind of, I think it's better to write it down. So y, the surface y equals 0, the surface z equals 2, and the surface x equals -1, x equals 1. Okay, so you want to do this sort of scalar. We want to find the volume. How do we find a volume of any surface? We integrate, right? What is the density in this case? The density is unity, 1. Right? If you assume there is something that's 1 per meter cubed, how shall I say it? If you're integrating something that's 1, no units, and you do dv has units of meter cubed. So when you finish the integration, you get meter cubed. You get volume. So you assume a scalar field that's unity in space, and you integrate over it, and that gives you the volume of the air of the space you're integrating. Okay. So to simplify matters a bit, what we want to do, this is a little bit complicated to see. What we want to do is we want to project volume sections into the XY plane. So, so let me draw just the XY plane. So this is the XY plane. At any Z, I haven't specified what Z is here. This is just the XY plane at any Z. We know that there's a surface at x equals -1 and x equals -1 and x equals 1, right? So we know that this kind of, let me draw the sphere first. The projection of the sphere is going to be this thing, right? We know there's x -1 and x plus 1 surface. We're looking at those surfaces from the edge. And what's the total extension of this surface? It's the sphere, right? So it reaches this point. What is this point? This point is x. What is the equation of this circle, by the way? Equation of this circle is x squared plus y squared equals 16 minus z squared. So this is a circle that's going to have varying diameters, radiuses, depending on where the xy plane is, where you, what slice you're counting, right? So this would be the circle, and this would be, y here is going to depend on x. So y here, what the point y here is going to depend on x, of course. Depending on x, we're going to reach a certain extension. So this is kind of like the slice. So we want to do the volume integral by converting it into sort of a surface integral. We're going to find the surface of every slice and then sum it up to get the volume. Of course, there are other views. So this is the view from the XY plane. This is the view from the ZY plane. Right, so I have Z, I have Y. What would the view look like? Well, I said it's also a sphere, right? A sphere is symmetrical. From whatever angle you look at, you'll see a sphere, right? So I see a section of a sphere, a slice of a sphere, but how wide the slice is going to depend on what x is, right? Because x could be anything here. So this equation of the sphere is going to be y squared plus z squared equals 16 minus x squared for any fixed x. Right? So depending on where x is, the slice will have a different radius. And then we said z equals 2. So this would be z equals 2. This would be the slice we would be integrating from that point of view. And then thirdly, zx plane so this is going to be x, and this is z. I guess I could do it that way. Or I could do the x here, doesn't matter. Yeah, I'm looking at it from the side, right? So again, same thing. The circle, the slice of the sphere is this, and it has an equation, x squared plus z squared equals 16 minus y squared. And again, we're going, we said z equal 2, right? So we are at z equal 2 here. Right, but and then x, yeah, I forgot about x. Z equal to, not only z equal to, x goes from -1 to 1. So really we are limited here from -1. Right, so this is z equals 2, and then -1 to 1, 1, -1. So this would be the slice, and it goes all the way down here. on the sides, x is between 1 and -1, and then z from 2 to the extent of the circle. All right. A word of warning: there is a bug in the way the textbook evaluates this. I don't think it even get the correct answer, but I'm not sure. I don't remember. But I definitely know that there's a typo in the way they incorrect way the way they evaluated this. So this is how you should evaluate this. This is going to be a volume integral. You're finding a volume. So we said we're integrating unity over the whole volume. And this is really the trick here for kind of like finding the volume is determining the limits of integration. This is this is a problem of finding the limits of integration. So this is going to be really dz, dy, dx. The question is now, what are the limits of integration? Where does z go from, right? Yeah. So x, where does x go from? From what to what? X goes from -1 to 1, right? X goes from -1 to 1. Y, where does y go from? From what to what? Right? X goes from -1 to 1. Y goes according according to this equation, right? So this goes from 0 to square root 16 minus x squared. Let's start with z, actually, just to make it simpler. Let's start with z. Where does z, so let me see. So this is, let's start with this third slice, right? So I can write z as square root minus square root 16 minus x squared minus y squared, right? That's from the volume, from the equation of the sphere, right? X squared plus y squared plus z squared equals 16. Therefore, z squared is either z is going to be plus minus. I'm going to have two it's going to have a positive part here and a negative part. So it's going to be plus minus square root 16 minus x squared minus y squared. Okay. So this is what. So let's say we start using this. We start from the bottom part here. So we start from minus 16 minus x squared minus y squared. This will go to some limit. The thing is, what the limit that this is going to go to is going to depend on x and y, right? It's not going to be let me see. No, this is actually, maybe I made did I make a mistake somewhere here? I don't think so. This is kind of confusing, but so it's going to some function of x and y. What is that function of x and y? If x and y, let me see if it comes back to me, is 2, yeah, it's 2, f x squared plus y squared less than 12 is going to be square root 16 minus x squared minus y squared f x squared plus y squared larger than 12. I might be the one who made them. Yeah, the reason I'm thinking, I'm thinking this doesn't make sense. This is correct, absolutely, if x squared plus y squared. What is x squared plus y squared? Think about it. Equals something. It's an equation of a circle, right, on the xy plane. So this is a sphere. This is a sphere. Yeah, ignore what I said. I think I'm the one who kind of got confused about something. So this is an equation of a sphere that has a radius of 4. So any cross section of that sphere, at most, is going to have a radius of 4. It's impossible for you to have a radius larger than 4, right? And what's 4 squared? 16. Oh no, maybe I didn't do a mistake. Something is special about 12, actually. So yeah, no, this makes sense. But there's something I'm trying to remember. There's something special about 12. Go over it, see if there was a mistake somewhere, because this was confusing even last time. But so let me in the interest of time, let me continue with another example, and then I might go back through this in a supplemental supplemental session. But yeah, that's the problem with trying to imagine things in 3D space. It's hard, but let's do another example. So this is to be continued. I'll do a supplement, seeing maybe I was wrong, maybe the textbook was right after all, but I don't think so. I remember when I taught this last time, I was pretty convinced that the textbook was wrong somewhere. All right. Same thing, we want to calculate the volume. Section cut by the planes. So this is now in the spherical coordinates. So we have some sort of volume section cut by the planes theta equals pi over 6, theta equals pi over 3. So this is something that goes start at theta equals. So this is theta equals pi over 6, and then this is theta equals pi over 3. Theta is going here, down here from the z-axis. And then phi goes from 0. Phi goes from 0 to pi over 3. So phi starts at 0. So this is the segment, and we go to pi over 3. So this is sort of this kind of segment that we. Right. So it's like what is R, by the way? R does not matter. Well, R matters because we are intersecting. Now we are taking this segment and intersecting it with the sphere x squared plus y squared plus z squared equals 16. So this is a sphere of radius equals 4. Now this sort of thing is going to be easiest to do in spherical coordinates. So in spherical coordinates, what are the elements? The elements are well, first we're integrating unity, right? So it's going to be r squared sine theta d phi d theta dr. This is just the volume element. Remember, we did that in a previous lecture, and then we're going to integrate that over phi, theta, and r. Notice that things are much simpler in spherical when we have spherical symmetry, because now to represent a sphere, simply r is going from 0 to 4. That's it. We're done. Theta is going from 0 to pi over 3, and then phi is going from 0 to pi over 3, and then theta is going from 0 to pi over 3. Sorry, theta is going, I believe, from pi over 6 to pi over 3. And this is it. This is the volume of that. It's like you take a sphere and then you kind of take a slice out of it, this sort of wedge from it. So this is going to be, I guess we can start with d phi. There is no d phi, right? So this is going to be pi over 3 simply. So this is going to be pi over 3, pi over 6, because there is no phi here, so it's going to be a constant. R squared sine theta d theta dr. We know how to integrate sine, right? So this is going to be pi over 3, 0 to 4, r squared, take it out. No, I cannot take r squared out. R squared, and then I integrate sine theta. It's going to be minus cosine theta, going from pi over 6 to pi over 3, dr. And then when you do this calculation, this is going to be pi over 3, and then this integral, this evaluation is going to be minus half plus square root 3 over 2. And then you integrate r squared dr, which is r cubed over 3 from 0 to 4. You do this calculation, it turns out it gives you a number. It gives you 8.177 meter cubed. All right, and that's the volume integral. You won't see many examples of a vector volume integral. It's not very common. When it comes to integrating over 3D space over a whole volume, it's more common to integrate scalar functions. All right. Let's see how much time we have. Oh, you have a difference in. Okay, we have 10 minutes. So I want to now, we're gonna, so homework 2, we have, I think, a problem with line integral, We're gonna do a bunch of integration problems. And anyway, I mean, you're gonna also practice this. The point here is to understand how to do the integration mathematically, but ultimately in the context of EM theory itself, we're going to do some integration. So, all right, now to the kind of like nice, well, more interesting part of vector calculus, which is differentiation. Integration, we needed to do that because we needed to know how to integrate. Remind ourselves how to integrate, and we need to lay the background. And we said the background is a fundamental generalization of the fundamental theorem of calculus. Right? So because there are 3 kinds of integration, because there's a line integral, and a surface integral, and a volume integral, naturally you can sum over a line, over a surface, over a volume. It's easy to understand. However, what's more subtle is that because we have those 3 different kinds of integration, that will lead to 3 different kinds of differentiation. And those 3 different kinds of differentiation are the gradient, and then the kind that arises from surface integral is what's called the curl, and then the kind that arises from the volume integral is what's called the divergence. And the relationship between those 3 different kinds of integrations and differentiations is exactly the relation entombed by the fundamental theorem of calculus for integration and differentiation on a real line. So we talked about that last time. So let's start with the gradient. Right. The idea is to use the fundamental theorem of calculus to define this form of differentiation. So the line integral from 2 points in space, as we define it, as we understand it, point 1 to point 2, I could integrate on multiple curves. It's something like this. F, I have some vector field F. F dot dl equals, right? Now, using the fundamental theorem of calculus or as a template, I want to hope that, hey, I can write this integral from P1 to P2 as just something that depends on the boundary. Can I do that? Right? So, by the way, if this integral depends only on the boundary, meaning depends only on P1 and P2, this is instantly a conservative force. Why? Because the integral is going to be the same regardless of the path. If I take path 1, L1, or L2, or L3, or L4, if this is a sort of integral that depends on the endpoints only, by definition, this is a conservative field because you go one way and then you go back, you get 0, right? So taking again guidance from the fundamental theorem of calculus in one dimension, we would like to write this as some function that depends on the endpoints only. So this is some function of P2 minus the same function of P1. Okay, so we want to write this integral as this. Now, what would this function be? We want to hope that this function can be derived from F, from the field itself. So we hope that this function is something that we can get through an operator, in the same way where differentiation was the operator that gave us the capital F function. Here we hope that U can be derived from F by some sort of operator. So I could say operator F, right? But I don't want to write it this way. I want to give you the final notation. So we write this as this symbol. It's called the nabla F. Nabla U, sorry. Yeah, I'm hoping that I can write F, derive F from U. So first, I'm hoping I can write this integral as this thing, which is similar to the fundamental theorem of calculus, well, analogous exactly to the fundamental theorem of calculus. And then I'm hoping I can get F from this U through some sort of operator. And so I can, some operator where I plug in U, which is a function, scalar function in all of space, and I get F, which is a vectors function for all of space. Right? And that's it. That's enough to define, believe it or not, that's enough to define what nabla U is exactly. Right? Because we can plug that back in, and we can use the interesting property of the differential integration, in that we can integrate back to smaller and smaller and smaller paths. We don't have to integrate over a long path. So I can write this as P1, P2, instead of F, nabla or grad U dot dl equals U, P2 minus U, P1. And that's enough to define the gradient, because I can make now P1 as close as I want to P2. I can make the 2 points as close to each other as I want. If I make them really close to each other, something curious happens in the integration. This becomes a constant. So I can take this out. I can write this as P1, P2. I can write this as I guess, what can I write it as? Let me see. I can, well, first I can do the linearity of the dot product, right? So I can take this out. So this is going to be, right? So remember we said if we have A dot B plus C plus F, this is going to be A dot B plus A dot C, blah, blah, blah. So if you have a sum A dot F, so if you have a sum of dot products, you can always take a common term out. You can always do that, right? So when I make P1 and P2 really close to each other, this becomes a constant. This becomes a constant, so I can take it out. So this is a sum of dot products. So this becomes delta U dot P1, P2, DL, right? I can only do this, by the way, only if P1 is approaching P2. I cannot do this if P1 is far away from P2 because this becomes variable. This depends on where you are in space. Only because P1 is really close to P2, this becomes a constant. So I'm summing like a product. I can take the common factor out. That's a constant. That's what I'm doing here. That's the only reason I can take it out. And this approximately equals U P2 minus U P1, right? What is this? Let's divide this. This is delta L, right? So this is some vector in the direction. So here I'm summing the line element dl over this path from P1 to P2. So this is a vector that has a length of delta L. So this is a vector that has a length of delta L. And it's in the direction between P1 and P2. So it's in the direction of the unit vector between P1 and P2. So this is a unit vector, right? Equals this. So I can divide by delta L. I end up with delta grad U dot the unit vector in the direction from P1 to P2 equals U P2 minus U P1 over delta L. And that's it. This is what the gradient is. The gradient is the directional derivative. If I have U, a scalar field, and I take its gradient, the gradient gives me a directional derivative, which is a vector field that if you dot it with any direction, it will give you, let's say you dot it with this U hat, right? It will give you the rate of change of U in that direction. If you dot it with some other direction, it will give you a different rate of change, which is the rate of change of U in that other direction. So grad V is really the directional derivative. That's essentially what it is. Assume you are passing point P. So let's say you are at a point P, and you assume you are on a certain path. You know, you are moving in a certain path, and you're passing the point P with a certain velocity v, right? So v is clearly, let me see. Let's call this delta lambda, this vector. Essentially, delta lambda is the vector between P1 and P2, just terminology. So this vector between P1 and P2 is delta lambda. It has a magnitude of the distance between P1 and P2, and it has a direction from P1 to P2, right? So so the velocity going through that point is just going to be delta lambda over delta t, assuming the 2 points, you're really close to that point. So this is another way of formulating it. Another way of formulating it is that I take the delta L back here, and I have here delta lambda, right? But we said delta lambda is V dot delta T, so I can take delta T back, right? So this is going to be UP2 minus UP1 over delta T equals du by dt. So this is another interpretation of the gradient. If you have a field and you take its gradient, and then you dot it with the velocity at a point, this tells you the rate of change of that field at that point. Let me give you a very concrete example. If I give you a scalar field, a temperature field, a temperature in the room, and I tell you, hey, it's a scalar field, you can take its gradient. Take the gradient of that field, that will give you a vector field, If you take that vector field at a certain point and you dot it with a velocity at that point, that means like a particle or a small, really tiny person passing in that point with that velocity is going to feel this certain rate of change of temperature. If you increase the velocity, you're going to feel a larger change of temperature because you're moving faster. But if you're moving at the same speed and you increase the gradient, you'll also feel a faster change in temperature because the temperature is more gradient. It has steeper. The change in the temperature is steeper. But this is the interpretation of this thing. This is the are we out? Okay, sorry, I kind of forgot about the clock. So, okay, so this is a good introduction to the gradient. We're going to talk about it more next time. And let me see. All right, everyone. I'll see you on Friday. There's no time left. Thank you. Stop this.